Yes.
I'll give it a go. So the three carbon molecule from carboxylation is converted into. I'm trying to remember how they worded this.
We don't need names. What happens to that carbon molecule? So you started very well. So the three carbon molecule.
I have in my notes that it was converted to a 3-carbon carbohydrate.
Yeah.
By enzymatic reactions that were produced from or driven by the ATP in the end.
Yes. So basically, that's what is happening. So what you have now is what you have is this carbon molecule from here is going to be reduced. Right? How is it going to be reduced? With energy, because again, you have to input energy to reduce the molecules. So you're going to use ATP and an ADPH that is going to donate electrons to reduce the weight. Okay, so this carbon molecule is now reduced to a carbohydrate. And then what happens in regeneration? Yes.
So it's a regeneration of ribose, like I think 10 reactions.
Yes, it's a very complex. So what are you regenerating, like in general terms?
I just had written down ribose.
Right. Yeah, very complex. How many carbons is that molecule? Do you know? Roughly. Ribose. How many carbons? So look at this diagram. What would you need to regenerate to continue the cycle? You're gonna, after this, you're gonna start this again. What would you need to regenerate? Of what? Yes, so you're regenerating that 5 carbon molecule. So that ribose 1,5,5,4,8, whatever the long name is basically this 5 carbon molecule. So you are taking, the plant is taking 1 CO2 from the atmosphere. And finally, in the list. So you have 1 carbon, 1 CO2 from the atmosphere, joining a 5 carbon molecule. And then that gives you 2 molecules of 3 carbons. They are reduced to carbohydrates. And then you have to regenerate that 5 carbon molecule to continue this. So that means that the CO2 that you have here, from all this cycle, you only fix 1 CO2 into 1 carbon of sugar. Why? Because you have 6 carbons here, right? But then you need to take 5 to regenerate. So each one of these cycles is only really fixing 1 of them. So in carboxylation, right, you have the 1 carbon from CO2 and the 5 carbon molecule giving you 6 carbons. Then you reduce them, and then you have to regenerate this here, right? 5 carbons. So again, just even over more simplified cycle, 1 CO2 joins 5 carbon, you have 6 carbons. In reduction, you're not changing the amount of carbons, you're just reducing them. So from one state to a more reduced state here. And here what you can see is that 1 carbon, the plant keeps 1 carbon. And then says, okay, from these 6 carbons, I can only keep 1. So multiple reactions happen in this process. The plant keeps 1, and the 5 carbon are regenerated, and that's what it has. You just have energy input here. This 1 carbon gives 1, so of course, I'm not saying it's exactly the same carbon, but the net output is going to be 1. And a lot of energy is going to be processed.
Is it just one of them?
Yes.
So 2 heading DPHs and 3 ATPs.
Yeah, so 2 ADPH and 3 ATPs. And then, basically, I'm not going to give you an entire equation, it doesn't matter this one. But as you can see, to fix each one of those carbons, that's why we talked about the output of the light reactions doesn't leave the chloroplast. It goes to feed, to power the carbon reactions. And I'll show you the rest of the equation later on, but I want you to focus on this. The oxidation of these 2 molecules of water give you enough energy to fix one state. Okay, so that output, in theory, if everything works as, math, chemistry in a book, it should be a direct balance of everything. So I think with your notes, you're probably capable of doing this. So I want everybody to give this a try. So how many CO2 molecules need to enter the Calvin cycle for the plant to synthesize a triphosphate, which is how a glucose molecule, sort of. And then how many times does the plant need to run the light reactions to synthesize that triphosphate? Yes.
Is it 6?
6 what?
So I know it's 6. I don't want to answer B before we're on B, but I know it's 6 to run per 6 CO2 molecules are needed.
To produce a triphosphate. So a triphosphate is 3 carbons. So like half molecule of glucose, a molecule is 6 carbons. How many CO2 do you need to fix to produce a 3 carbon carbohydrate?
Wild guess 18.
No. I mean, why do you say 18?
Just because, so it takes 6 CO2 to do, you said 1, I just multiplied 6 by 3.
So if you look at this one, how many carbons need to enter the Calvin cycle for a plant to release a carbon? It's 3 carbon sugar. Remember, this molecule is recycled. So how many CO2 need to enter the Calvin cycle for a plant to release a 3 carbon sugar?
It's 1.
No. Justin raised his hand first. Yes.
So it's going to be 3 carbons because you're going to fix one each time you do it. But it's going to cause you to have to do
the light reaction 3 times because you need the 9 ATP, which means you're going to have to do it 3 times. You get 3 per run, and then you have to do 6 MeV/pH, which is also you get 2 per run, which is 3.
Yeah, so to clarify that, Nick, so I think you were probably overthinking with the 18. Each CO2 gives you 1 carbon of sugar, right? So if you have 3 carbons coming in, it gives you 3 carbon sugar. If you have 6 carbons coming in, 6 CO2s will give you 1 glucose. Each one of these carbons will, again, not the exact same carbon, right? But all of these complex processes will at the end give you 1 carbon that is going to be reduced in the form of sugar. Okay? So if you have this carbon here, let's say, it's going to give you this. So if you have 3 here, you're going to have 3 out. If you have 6 CO2s, 6 carbons or glucose. If you have 12 carbons, that would be 2 glucoses. Okay? So just it said 3 CO2s will give you, if everything works as in theory, 1 3 carbon sugar or 1 molecule of glucose. And yes, how many times does a plant need to run the light reactions? It would be 3, because remember, every time the plant runs the light reactions, gives you enough energy to fix 1 CO2. So it runs the light reactions once, it gives you enough energy to fix 1 CO2. If you run the light reactions 3 times, it gives you enough energy to fix 3 CO2. If you run the light reaction 6 times, then it's 6 CO2 for a molecule. Okay. Does that make sense how we are converting? More than the numbers, because this equation is everywhere. It wouldn't need you to ever memorize this. But more to understand how they are connected, how the output of one feeds into the next one, and how this whole thing basically why CO2 is going to be so important for the plant, because each one of these CO2 molecules will eventually become 1 carbon of carbohydrate that the plant needs to then take to the cytoplasm and do glycolysis, and then take to the mitochondria and do the Krebs cycle, just as we do. So it takes energy for the plant to release energy. So, 1 CO2 basically gave you more than the numbers, but from one of the runs. So 3 CO2s would be 3 of these runs. And so that's what the overall equation of the carbon reaction is. Anybody else wants to give it a shot? Okay.
So basically, fixing carbon can also be dependent on light reactions, and that can be through multiple different ways. So like in Rubisco, it requires transpiration to have a constant concentration of CO2, because CO2 is like a catalyst essentially for Rubisco, as well as the intermediates of photosynthesis need to be present for the Calvin cycle to be constantly run. And I'm pretty sure some enzymes are regulated by ferredoxin, which is produced in the dependent reactions of photosynthesis. So instead of producing an ATP, it can produce, I think, a few different enzymes to activate them, essentially. So all of that essentially means that during the day, the Calvin cycle is going to be much more active than during night.
Yes. So basically what happens is many things. The light directly is required to activate some enzymes of the Calvin cycle. The light is required to transcribe or to initiate the catalytic activity of Rubisco. So in the absence of light, Rubisco might be there, but it's not like its active way. Also, some enzymes can be turned on in the presence of light, and if light is not present, they are just going to remain on. And some of the products of the light reactions are also important for activating and running the cell inside. So there are multiple enzymes, I'm just showing you. Light can directly activate Rubisco and can directly activate enzymes. Basically, Rubisco is the carboxylation phase, in the reduction phase, and in the regeneration. So different enzymes of the entire process need light to be activated. The details of how each one is activated is not really important. I just have this here because it can also, does everybody know what post-translational modifications are, roughly? So sometimes when proteins are translated and you have the amino acids, there are some modifications, like for example, glycosylation. Some things that happens to the enzymes once they are translated. And so there's just some of these modifications that make them active and specific that only happen in the presence of light. So that's important as well. And so I know Lucas briefly mentioned this, but give it another try. How does the ferredoxin regulate the Calvin cycle? Yes.
It reduces the electron transport chain as well as two chloroplastic proteins to regulate four ions, fructose. It's just four things that are like that.
So, okay, so let's go. What is ferredoxin? What would you tell me? What is ferredoxin? How does it work? I mean, where is ferredoxin? Where do we find it? I mean, when have we talked about ferredoxin?
Ferredoxin is it's top photosystem 1.
Yeah, so it's part of the light reaction,
Yes.
right? It's something that is important in the light reaction. So how is ferredoxin doing all of that you said? What happens in ferredoxin?
I assume it stops the electron gradient from going through.
So you said ferredoxin. So ferredoxin, when you look at the light reactions, is here, right? Reduce ferredoxin. It's the last thing that is reducing the light reaction.
Yes.
So what does this ferredoxin do? How does it activate? How does it regulate the Calvin cycle? So you said four things are regulated. So
yes. Sorry, all I know is that it reduces the chain.
yeah, so it reduces a bunch of things and
It's not the electron transport chain, I don't know.
it's not the electron transport chain because it's not an electron transport chain, but ferredoxin reduces the four things that you talked about that I don't care what they are. I don't know what they are. Four things, and then at the end of that reaction, what happens?
It stops. Sorry.
So you said ferredoxin is reduced here, and then it reduces four different things. Right?
Yes.
And then how do so it reduces, say you have ferredoxin here, and it will reduce 1, 2, 3, 4 things. How do these things, or how does this control or regulate the Calvin cycle?
But it stops the production of phosphokinase, and then the NAD glyceraldehyde, so it makes it so it doesn't have the fuel to go on. But
So
sorry,
you're,
that's not what you're looking for.
no, you're almost, I think you're almost there. So reduced paradoxic reduces these things. So usually when you have something, let's say when light is controlling activity of something, light has to do, I mean, I guess I'm more concrete, how do these things regulate the Calvin cycle? So
Yeah.
paradoxing is reducing these things, and then what do they do to the
Yeah,
enzymes of the Calvin cycle?
They deactivate the CO2 acceptor? No, I don't know. I'm gonna pass it off.
So almost, you're almost there. What do? If they control the Calvin cycle, they either activate or deactivate the enzyme, right? So the reduced paradoxing activates or deactivates the Calvin cycle.
Yeah, sure.
So think about it. Reduced paradoxing. Will this, once you have reduced paradoxing, will this turn the Calvin cycle enzymes on or off?
On?
On, yes. Because we said that light is important for all of this, so you will turn them on. Okay, so the reduced paradoxing will reduce things, and those reduced things in turn will reduce something that turns the enzyme on. So that's the whole thing. So the overall message is you need light and something reduced. So you need light and this reduced paradoxing here, which is this last product, to reduce four things that we don't care what they are, to basically once your enzymes or those enzymes in the Calvin cycle that are activated by light, when they are reduced, because paradoxing is reduced and that reduce something and that reduce something and that reduce something. When the enzymes are reduced, they are active, but if they are oxidized, they are inactive. And that's how light, by reducing paradoxing, will reduce the enzymes that are going to be activated by light. Yes?
So generally, in the plants that are fixing carbon at night, like C4 plants?
Chem plants.
Okay, camps, right. Are they using like different enzymes? Or are they just like less efficient because they're not as
They
activated?
have a different activation system, and we are going to talk about chem photosynthesis later. Yes.
Okay.
So they have a different system in which they store some of these reduced compounds and release them at night to activate certain things. Yes. So this is complex drawing to show you that only when light is present, you're going to have paradoxing in a reduced state to reduce it. That's it. So not all, but many of the Calvin cycle enzymes are only active when certain parts of them are reduced. So again, reduce paradoxing, then reduces the regulatory enzymes, which reduces the target protein, which activates the target. And then when there's no light, paradoxing is oxidized because there's no electron cycling, because there's no photosynthesis happening. So these specific bonds here, these cysteines actually, are oxidized, and then protein is inactive. Yes.
So is light also directly activating the group visco and those other enzymes?
Yes.
Okay. So,
Yes. So these are some of the enzymes. Actually, the Rubisco one is more complex. So Rubisco, all of this is acting in the chloroplast, and so Rubisco is very large, and actually just because large. So Rubisco has different subunits, and it's so complex that part of Rubisco is encoded by the chloroplast gene, and the other half by the nuclear gene. So light has to activate both subunits and then bring everything to the chloroplast, and only then the full Rubisco is active. So why is half of Rubisco in the nucleus and why half of the chloroplast? I don't know. That is just, Rubisco is just very complex, and both subunits require light to be activated. So Rubisco also needs light. This is more like, not chemistry, but yeah. So why specifically oxidation and reductions of cysteine? How is this? So what is reduced and oxidized are these groups, sulfhydryl groups of cysteines. How is so cysteine? This was an amino acid. Why is cysteine reduction and oxidation of cysteine regulated? Yeah, so cysteine is the only one that has an SH. Well, finally also like somewhere. Why is cysteine? How does reduction and oxidation of cysteine specifically activate and oxidize? Activate and deactivate enzymes. Everybody that's raising your hand, you already have 2 points. Oh no, Justin, were you raising your hand? You only have 1 for today.
Okay, sure. So for if it's reduced, then it can actually go to help produce the substrates because it can drop off a hydrogen. But if it's oxidized, it can't. So it wouldn't be able to continue to go to produce the products because it didn't have an oxygen. Right?
I mean, yeah. So cysteines do something specifically to protein conformation. Yes.
So when cysteine is reduced, you have a hydrogen attached to the sulfur, which is generally when you break your disulfide group, which is like a really strong bond in any sort of protein. So if you break your disulfide bridge, you're likely going to have a conformational change in the protein, and it's either going to activate it or deactivate it depending on the protein. And I believe the protein that is oxidized in photosynthesis is going to be deactive. Whereas once it's reduced in the body as protein, that activates the protein through conformational change.
Yeah, so the key is conformational changes, okay? So of course, Lucas was more detailed than my drawing, but tertiary and quaternary structures of protein. So the whole protein conformation is maintained by different bonds, like ionic bonds and van der Waals forces and hydrogen bonds, and one type of covalent bond, which is disulfide bridges. Disulfide bridges, since they are the only type of covalent bond that maintains conformation of a protein. So remember, in a protein, yes, the amino acid sequence is important, but also how the protein is folded, properly folded at the end. So protein decides this is the figure, and it's maintained the 3D structure by different bonds. One of them is disulfide bridges. The only amino acid that can form disulfide bridges is cysteine. So, as Lucas was saying, so when you have the oxidation of when your cysteines are oxidized, you basically have the disulfide bridges formed. Okay, simple. So, have this disulfide bridge form, and probably here I'm trying to represent the protein has this particular structure. Once you break those bonds, the structure of the protein might change. And it's that conformational change that is deciding this is the inactive form and this is the active form. All because of conformational changes directly related to disulfide bridges. Okay? So, reduction and oxidation observed. So you know how sometimes proteins can be activated or deactivated because they are phosphorylated or dephosphorylated. That's one way in which you can activate or deactivate proteins. This one is either forming or breaking disulfide bridges. That changes the conformation of the protein and tells you when you're active or you're not active. Okay. So rubisco is the most abundant enzyme on Earth. It catalyzes the carboxylation, right? We talked about this carboxylation in the Calvin cycle. So you have the 5-carbon molecule, you add the CO2. I recall because, of course, I remember hopefully everything I said in this class, that before midterm 1 or 2 something, we briefly talked about something about rubisco, and I told you rubisco can do 2 things. It can do what it's supposed to do and can do the wrong thing. So I don't expect you to remember that, but this is the point when we're talking about it. Rubisco is supposed to do this. It's supposed to have this 5-carbon molecule, grab the CO2, put it together, and do everything with it. But sometimes rubisco messes up. And instead of doing this, it binds oxygen. Instead of binding CO2, it binds oxygen. Yes.
Isn't it photorespiration?
Yeah, so it's called photorespiration. And what are the consequences of this?
Doesn't it like stop the photosynthetic process?
Yes. Can you tell me roughly why or anything else you know about that?
It stops it because instead of binding to carbon dioxide, it binds to oxygen.
Yes. And
I know it has something to do with electron flow, right?
so let's walk through this. So you have these 5-carbon molecules. Oh, I actually have it. So let's just almost there. So just one more thing. So you have the 5-carbon molecule cycling. You add a CO2, and then you have 2 molecules of 3 carbons, right? 5 and 1. Right, you have these 3 carbon molecules. If instead of binding another C, you bind an O, what happens? What are you going to produce? Instead of 2 molecules of 3 carbons.
Starts with a G.
Oh yeah, no, yeah. So you're again over thinking. So if 5 plus 1 gives you 2 molecules of 3 carbons. If you don't bind a CO2, but instead you bind an O, what do you produce at the end? Instead of 2 of these things, what do you produce? Does that make sense? You have 1 CO2, and then these 5 carbon molecules, and you produce 2 3 carbon molecules. If this 5 carbon doesn't bind to this, but binds O2 that doesn't have carbons, what do you produce instead of this? You didn't add another carbon, what do you produce?
It would just be 5 carbons and 2, right?
Yeah, it would be 5 carbons. So instead of producing this, you actually produce this. Okay? And this is what stops photosynthesis. This product is toxic to the plant. The plant cannot let that accumulate. That is what photorespiration basically is. And so instead of doing a carboxylation, rubisco does an oxygenation reaction. And instead of producing the normal substrate for the Calvin cycle, that is going to be reduced and then give you triose phosphate, it gives you two carbon molecule. And this two carbon molecule is a problem for the plant. Can't be used in the Calvin cycle. So, anybody tell me in your own words, then in summary. The last one. How is the plant specifically affected if Rubisco instead of carboxylated? That's the wrong thing and binds an oxygen instead of a carbon. Yes.
It just wouldn't be able to make the sugars it needs, or without like greatly drastically reduced.
Yeah, so what does that mean for the plant? So it cannot make the sugars, and what else? What else happens?
And you have like the buildup of like a toxic product, which is also be reducing the efficiency and won't be able to respire, like, obtain the energy from like those glucose molecules that it's building.
Yeah, so basically, two things happen. The plant, all the way back, but just regenerating this carbon molecule was a lot of energy, right? The plant spent energy just going through this to regenerate this. If the plant spent all of this energy and Rubisco messes up, and instead of adding this, that's something that cannot be used. The plant wasted, the energy that is spent regenerating that carbon molecule is wasted because there's no CO2 phase. You bound the wrong thing, and I have no carbon for this round. And now I have to do all this process again just to regenerate the 5 carbon molecule. So it's a waste of energy for the plant because Rubisco messed up and grabbed the wrong molecule. So it's a waste of resources for the plant. And the other thing is